Let's take an example to see how we can use these equations here. So this example says we have a gas. This gas at 450 degrees Celsius, 0.5 megapascal, flows at steady state. So steady state, this one means we have no change in the properties with respect to time, which means any accumulation term, if you will use first law of thermodynamics, second law of thermodynamics, entropy equation, any accumulation term, you can substitute it with zero. This gas flows at steady state through an adiabatic. Adiabatic means Q equals 0, and reversible nozzle. Reversible adiabatic together, these two words are equivalent to something called isentropic. Remember from previous examples, an isentropic means what is constant? Entropy. So according to this description here, reversible adiabatic, so this is equivalent to isentropic. And isentropic means entropy is constant, and the entropy generation term, this is equivalent to 0. There is no generation of the entropy. The existing pressure is 0.1 megapascal. Find the velocity, find the temperature of the existing stream. We have solved this example in previous lecture. We solved requirement A for this example. But here we have requirement B. It says this gas is ideal gas, and the heat capacity at constant volume CV is 3R. R is constant, 3 is constant. So here, according to this statement, it tells you we have an ideal gas and also we have constant heat capacity. Then we can use any of the equations that we just showed right now. The molecular weight is 75 kilogram per kilomole for this gas. So we need, again, to find velocity, we need to find the temperature. So what we will do in this example, so again, in order to solve this example, this is like similar to what we did in the previous lecture. So we need to find temperature, we need to find velocity, so we need to start with the first law of thermodynamics. We did the derivation in previous lecture and we ended up with that the outlet velocity over 2. This is the inlet enthalpy minus outlet enthalpy. Previous lecture, when we solved this example, the gas was steam. So we get the enthalpy from the steam tables, we did the interpolation from the steam tables, but here he said we just have gas, so we can't use the steam tables. So we cannot, like, in contrast to previous one, here we cannot use steam tables to find specific enthalpy values. So what is the other way to calculate enthalpy? We have ideal gas, so the change of the enthalpy is CP/dT. So since we have ideal gas, then we can say dH is CP/dT. Okay, then we need to integrate this equation. So by integration, so we have delta H, which is H of the out minus H of the inlet is Cp T2 minus T1. Cp is constant, take it out of the integration of dt as T2 minus T1. Okay, so this is the equation we have. So what is given? We have CV, this is 3R. But in this equation, we need CP. So anyone remember the relationship between CP and CV for ideal gas? R. So we know that for ideal gas, we know that CP is CV plus R. So CP will be 4R. And also given, we know that T1 is 450 degrees Celsius. So we know the value of CP is given, T1 is given. So what is the value of T2? We have no idea. T2 is still missing. Then we can't use like this equation now to calculate delta H. So again, we need to find the velocity. In order to find velocity, we need to know the enthalpy change. Then we use the equation to calculate the enthalpy change, and we have everything in this equation except T2. So if you can find the outlet temperature, substitute in this equation, find enthalpy change, and then go back the first equation to calculate the velocity, and this is the requirement. So how can we find the outlet temperature? There is one information in the problem that we didn't use so far, which is this one. This process is isentropic. So isentropic means there is no change in the entropy happening in this process. Okay, and again, this is ideal gas with constant heat capacity. So we have an equation that we displayed right now. We can use any of these equations to calculate entropy change. So since we have ideal gas with constant heat capacity, then we can say delta S is CV, then T2 over T1 plus R, then V2 over V1. Or we have this one is CP, then T2 over T1 plus R, then P1 over P2. So these are the two equations for the enthalpy that we can use. So again, for any of these equations, you can solve it. So what we have here, we have delta S, the entropy change. This one will be 0 because we have the isentropic process. We know the value. Let's assume we will take this one. We know that CP, we just said CP is 4R. We have T1 is given 450 degrees Celsius. Or this is the ideal gas constant. So we can use 8.314 joule per mole Kelvin. We have pressure one. This is known. It's 0.5 megapascal. And there is no need to convert it to Pascal because in this equation P1 divided by P2, any conversion factors will be cancelled. And we have P2. This one is 0.1 megapascal. This is also given. So if you substitute in the entropy change equation, what is the missing variable? What is the unknown variable in the equation now? Find temperature. So in this equation here, this is the only variable that we have no idea about this value. So now we can substitute in this equation here. And after you substitute, then you can find T2, the outlet temperature. And the outlet temperature in this one will be 483 0.6 Kelvin. So now we have T2, then we will go to the enthalpy change equation. So now substitute in delta H, which is H out minus H in equals Cp T2 minus T1. We have all the variables here, so we can substitute in this equation, and we said delta H will be negative 7966.5 joule per mole. So now we can go to the first law of thermodynamics. That says the outlet velocity square over 2 equal H in minus H out. But just notice one thing. Here in the delta H equation, it calculates outlet enthalpy minus inlet enthalpy. In the first law of thermodynamics, we have inlet minus outlet. So make sure you consider the sign. Okay, because here we have difference in this one here. So here in this one, this term, H in minus H out, this one is equivalent to 7966.5 joule per mole, not the negative. Okay, because one equation it gives you H out minus H in, the other equation needs H in minus H out. So make sure that you consider this sign convention. So if you did this and substitute in the equation, then the outlet velocity that we have here, this one will equal to 460.9 meter per second, and this is the requirement that we need to calculate. So the equations that I have here, this is a good thing, that this equation, this shouldn't be specific. This should be like molar. So everything should be molar, not specific in the equation. Okay, so just consider this one. Everything in this equation should be mole. Cp we have here, this is per mole, so this delta H should be molar enthalpy, not a specific.